Hello students, in video number 3, which is class 12 electric flux and Gauss theorem, video number 3, we read about two application of Gauss theorem. First application is intensity of electric field due to uniformly charged spherical cell. That is very important. Uniformly charged spherical cell, that is made of conducting material. So now we see that this is suppose this is uniformly charged spherical cell. Suppose this is uniformly charged spherical cell. Spherical cell means hollow sphere. It is given plus Q charge. See that it is having some width. Its center is O. Suppose this is a spherical cell having radius R, capital R, and its center is O. It is given plus Q charge. Plus Q charge is spread all over the surface. Plus Q charge is spread all over the surface. Plus Q charge spread all over the surface. Now we have to find out the intensity of electric field due to this charge spherical cell. There are 3 points. To find out the intensity of electric field due to uniformly charged spherical cell, there are 3 points: outside of the spherical cell, on the spherical cell, and inside of the spherical cell. First we find out the intensity of electric field due to this charged spherical cell outside. Suppose any point P is at a r distance, a small r distance from the center. At this point we have to find out the intensity of electric field. For this, by the Gauss theorem, for this we draw a Gaussian surface, Gaussian spherical surface, taking small r as a radius and O as a center. This is the Gaussian surface. Now take a small area around P as same as the Gauss theorem. Take a small area around P. Suppose this is dA, and see the direction of electric field. See the direction of electric field. The direction of the electric field is this, just, and the direction of area vector is also. Area vector is perpendicular to the surface, and when we draw a line from the center to the surface of the sphere, it is always perpendicular. So the area vector and electric field are parallel to each other. Now the electric flux pass through this small surface, d phi E. D phi is equal to E dot dA. Vector E dot dA. This is the electric flux pass through the small area. The magnitude of E is A, E and dA, and the angle between them is 0, cos 0. Cos 0 is 1. So E dA, that is the electric flux pass through the small area. Now the electric flux pass through the whole area. Phi is integration of E dot dA by the Gauss theorem. So phi is equal to integration of the value of E dot dA is E dA, and we know that the electric flux pass through the closed surface by the Gauss theorem. Phi is equal to Q upon epsilon naught. You know that. Putting the value, phi is equal to Q upon epsilon naught. E taken out, dA. Integration of dA means whole area of the surface of this surface, that is dA is equal to A, that is 4 pi r square, Q upon epsilon naught E into 4 pi r square. The value of E is 1 upon 4 pi epsilon naught Q upon r square. That is the formula of intensity of electric field just outside of the surface. And when we want to find out on the surface, this point is and this is on the surface, so is in place of a small r we take capital R. So on the surface the intensity of electric field is equal to 1 upon 4 pi epsilon naught, small r is equal to capital R, 1 upon 4 pi epsilon naught q upon r square. That is, but when we find out the intensity of electric field inside at any point, so inside at any point, suppose that this is point P dash which is inside, and when we draw a closed surface passing through P dash taking O as a center, all charges outside of this sphere Gaussian surface, or you know that when any charge is outside of the closed surface, the electric flux passed through the closed surface is zero. So the electric flux passed through this closed surface, phi is equal to integration of E dot dA outside, but phi is equal to 0 outside. Phi is 0, 0 is equal to integration of E dot dA, and 0 E dA, E dot dA is equal to 0. Intensity of electric field outside of the spherical surface is 0. Inside of the spherical surface is 0. Intensity spherical cell, intensity inside the spherical cell is always 0 at any point inside, but outside is not 0. Outside is this, and on the surface is this. It is maximum on the surface, and as well as we go away from the surface, it is inversely proportional to r square. It is continuously decrease. This is the proof. Now next proof is the intensity of electric field due to non-conducting. This is made of conductive material, and when this is non-conducting, intensity of its second proof is intensity of electric field at any point due to uniformly charged non-conducting sphere. Non-conducting sphere. See that. Intensity of electric field due to uniformly charged non-conducting solid sphere. Due to non-conducting solid sphere. Okay, see that non-conducting solid sphere, when we give charge to non-conducting solid sphere, this charge is spread all over the volume. When we give charge to conducting sphere, the charge is spread all over the surface. Suppose this is non-conducting sphere of radius capital R, non-conducting sphere of radius capital R, it is given plus Q charge. Plus Q charge is spread all over the volume. So plus Q charge is spread all over the volume. Now we have to find out the intensity of electric field outside of the sphere at any point P, on the sphere, and inside. Suppose P is any point at a distance r from outside of the sphere, at which we have to find out the intensity of electric field. For this, again we draw a Gaussian surface taking O as a center and small r as a radius. Spherical Gaussian surface. जब हम अपनी तरफ से spherical Gaussian surface draw करेंगे, तो अगर different size की object है, when the size is in different size, or when the size of charge object is different, then we can draw a spherical surface. This is a spherical surface, and take a small area around T. See the direction of the electric field. The direction of the electric field is again this, and area vector is this, D. So the electric flux passed through this small area, d phi is equal to EDA, EDA cos 0, EDA, and electric flux passed through the whole area, d phi is equal to EDA. Same proof is, and by the Gauss theorem, phi is equal to Q upon epsilon 0, putting the value and find out the intensity of electric field. Intensity of electric field outside of the spherical sphere, non-conducting sphere. And on the surface is again small r is equal to capital R. We can put 1 upon 4 pi epsilon 0 Q upon r square. but the intensity is not the zero inside of the non-conducting sphere. See this. When we take any point inside of the sphere, suppose this is P dash at a r distance, r dash distance, and draw closed surface. To find out the electric field at this point, we draw closed surface. So the electric flux pass through this small area. Phi is equal to this spherical surface by the Gauss theorem, integration of E dot dA again directly, and phi by the Gauss theorem, phi is equal to Q dash upon epsilon zero, not Q, because some charge is outside. Total charge given to the sphere is Q, and some charge is outside, some charge is inside. Due to the outside charge, the electric flux passed through this surface is zero, but inside charge, the electric flux is not zero. Q dash, suppose that Q dash charge present inside of this sphere. We don't know the value of Q dash, but we take Q dash and eliminate it after proving it. Integration E dA Q dash upon epsilon naught. E is taken out, dA, and the value of dA, since the radius is r dash, that is by Q dash upon epsilon naught E 4 pi r dash square. So the intensity is E is equal to 1 upon 4 pi epsilon naught Q dash upon r square, r dash square, that is. But we don't know the value of Q dash. R dash is given, but Q dash is not given. So to eliminate it, we take the help of surface charge, volume charge density. Volume charge density is denoted by, you know that, rho. Rho is total volume charge density of whole sphere, that is Q upon 4 by 3 pi r cube, and the surface volume charge density of this small sphere, Q dash on the charge, and 4 by 3 pi r dash a cube. So find out the value of Q dash. Q dash is equal to Q 4 by 3 pi r dash a cube on 4 by 3 pi r cube, capital R cube. 4 by 3 pi cancel out. Value of Q dash is Q r dash a cube upon r cube. Now putting the value of this in this, so we get the intensity E is equal to 1 upon 4 pi epsilon naught. Q dash, in place of Q dash we put Q r dash a cube upon r cube, and r dash square, r dash cancel. E is equal to 1 upon 4 pi epsilon naught Q r dash upon r. This is the provement of this. That is the intensity of electric field inside of the non-conducting sphere. E is directly proportional to r dash. Inside you are seeing, and outside it is inversely proportional to the square of the distance. That this is the video number 3. Okay.